All right, next up we've got Ahmed Gharraph. Hey Ahmed, how you doing?
I'm very good, Chris. How are you?
Excellent. So give us a little background on yourself.
Quick background. So currently I'm one of the heads of CG at Framestore, Framestore IA Integrated Advertising. So we work on television, commercials, and immersive work. My background is kind of a bit of a mixed bag. I've been a generalist. I've been an effects artist. I've been a lighting artist. I've done character grooming. So as, you know, I've touched lots of facets of the CG world.
Excellent. Well, what's your presentation going to be on today?
So I'm mainly going to circle it around a commercial that we delivered last year for Purdey's. It's a short commercial, full CG. We had to create a hummingbird and a whole forest that the hummingbird lives in. We had to develop a new feather system in Houdini to do that. So I'm going to talk a little bit about that, talk about procedural geometry generating that helped us create this forest. And I'm going to talk about a couple of other projects that we delivered over the year in television.
Perfect. Well, let's jump in.
Hello again, and thank you for joining in today. As I mentioned in my intro with Chris, my name is Ahmed Gharraph, and I am one of the heads of CG at Framestore in London. Today we're going to take a look at a few of the projects that we've recently delivered and see how we've leveraged some of the tools in Houdini to help us create that work. We'll first take a look at how we brought to life a fully CG rainforest, as well as a quick look at some of the features of our newly developed feather system. We'll also look at some of the effects work that we delivered for the Netflix series The Witcher, as well as HBO's Watchmen. I should warn you at this point that there are some major spoilers ahead, especially relating to the work that we did for the Watchmen series. So if you've not yet watched this show and you don't want to see any spoilers, this is your warning to look away. Right, so before we get started, let's take a look at our latest show reel.
See no solution or exit out. I'm grinding it out, no one can see. The pressure's growing exponentially. I'm trying to keep up to speed with you. Your lane changing is absolutely me. I'm hitting the ground and I'm sprinting. I'm falling behind, now I'm tuning out.
We're good.
Okay, cool. So with the department that I help to look after at Framestore, we create content for all sorts of different mediums. Historically, we were mainly a commercials department, and while we still do create plenty of work for advertising, we're also now delivering work for television shows as well as immersive entertainment. such as content for theme park rides and location-based installations, like VR and AR experiences, that sort of thing. It's also worth noting that Houdini is at the core of our CG pipeline, and it's the main 3D software that we've been using over the past few years to help us deliver most of our CG work. So first up, I'm going to share with you some of the work that we did for a commercial we delivered last year. We were tasked with creating a fully CG jungle and populating it with a charm of hummingbirds. It was directed in-house at Framestore, and it took us a little over 2 months to complete, which really is quite a short amount of time to create something that's entirely CG. We quickly started by blocking out the entire commercial using existing jungle assets that we had in our asset library, as well as some basic geometry to represent the hummingbirds and their actions. As this previs developed, we started to get an idea of how much of the jungle we were going to see and which assets we were going to need to put more effort into improving, as a lot of the jungle assets that we had just weren't up to the level of close-up scrutiny that we were going to see in this commercial. So because of that, a lot of time and effort was put into prepping the assets that made up our jungle. We needed to bring the jungle to life by adding movement and as much organic detail as possible in the time that we had. And because we were shortchanged for time, we had to be quite economical in the solutions that we came up with. So to that point, we decided to use the good old wire solver to add movements to our plants. We rigged up the various plants using the find shortest path SOP, and we often did a two-step simulation where we would first sim the largest of the branches and the twigs, and then if it was necessary, we would then sim some of the smaller details such as leaves. We also generated a whole bunch of different volumetrics and volumetric sims and particle simulations to give the jungle more atmosphere and give a sense of pollen and bugs and insects that are floating around the air. One of the biggest successes that we had was all the procedural geometry that we ended up generating. Using the L systems in Houdini, we generated a small library of different types of foliage, which we then used to scatter over our different assets to add some really cool organic detail. I'll now show you a quick overview of how that was done. So here you can see some of the foliage geometry that we generated in Houdini. As you can see, it's quite simple and low poly. But because the end goal was to scatter thousands and thousands of these instances of geometry across our assets, it didn't really need to have a lot of detail. What was most important is that it needed to have an interesting and organic looking silhouette. So now we needed to create a setup to scatter our foliage across our various assets in a natural looking way. So we start off by measuring and mapping the various attributes of the geometry that is fed into the system. So things such as its height and curvature, how high up it is off the ground, which direction its faces are pointing, that kind of thing. We would then remap and manipulate this data to create masks, which we then used as a source to scatter our points across the surface. This is all kind of classic Houdini type work, right? You create a point cloud and then you instance some geometry onto those points. You then manipulate those various attributes on the points to determine things like the scale and the orientation of the geometry, that sort of thing. And of course, because of the procedural nature of this setup, once we were happy with the results that we were getting, We could then wrap up this tool into an OTL and quickly run any of our assets through it as and when we needed to. Okay, so onto our Hummingbird. As we all by now, having good reference and studying your subject is key when creating anything in CG. So we spent a very long time kind of collecting pictures and video references, as well as studying the various properties of hummingbirds. What size are they? How many feathers do they typically have? How does the iridescence of their feathers react to different lighting conditions? All of these things and all of this information feeds into how we decide to build and create our asset. Around the same time that we are awarded this project, we were also wrapping up on the initial development cycle of our brand new feather system. So this was a great project to test it on. It's been designed to work in a way which is familiar to Houdini users, in that it's not one all-encompassing tool or node. It's actually a bunch of nodes which can be combined to form this feather system. This allows the users to intercept the data flow at any point using native Houdini SOPs such as wrangles and VOPs, that kind of thing, for added control. And since Houdini already had a pretty comprehensive grooming toolset, we kind of leveraged that, and we decided to use that as the base to spawn our initial feathers. Another really cool design feature of the system is that it allows a seamless blending between any number of different feather designs. In this example here, we designed just 4 different feather shapes, which then blend between one another in an even distribution. Being able to design just a few feather shapes and drive how they are distributed and how they blend between one another allows us to create quite complex grooms very quickly and very easily. So here we can see a turntable of our hummingbird. And here's a close-up render of it. It was very important for us to do lots of animated renders to make sure that all the various parts of the bird were working together. To make sure things like that the feathers were stacking correctly and weren't stretching or deforming in an unnatural way, and that the shaders were behaving just as we wanted them to. And that's our hummingbird. And considering the short amount of time that we had to turn all of this around in, everyone was very pleased with the end result. So next up, we'll take a quick look at some of the work that we delivered for the Netflix series The Witcher. The majority of the work that we did was environments work and effects work, and we delivered shots for all 8 episodes of the season. As well as doing lots of environment extensions, we also created lots of fully CG environments. And this included creating the fortress city of Sintra, which we then had to burn down. We of course used Houdini Pyro for all of the fire and smoke simulations. And outside of doing the big kind of hero simulations of the buildings in the foreground, we also built up a library of different fire and smoke caches, which we used to populate and set dress the scenes with. Here you can see a breakdown of the full CG city that we built, and the effects elements as they're layered up in comp. So one of my favorite shots that we worked on for this show is this one. In this shot, one of the bad guys drops a box of evil worms onto the floor, and then these worms spill and flow out of the box and wriggle away to cause all kinds of mischief and mayhem. For this simulation, we used vellum strings in Houdini 17.5, and using vellum made it pretty simple to get some really cool results without too much effort. Here's an early flipbook of the worms as we were developing the setup. In the first few iterations, we created a setup using the tetrahedron fibers and contractions and that kind of stuff to simulate muscle movement. But we quickly discarded that approach and just opted for the simple noise field that affected the vellum strings. We found that this was enough to give the worms the impressions that they were alive, and it also gave them this erratic and menacing motion, which really fit in well with the story that we were trying to portray. To create the individual worms, we started with simple straight curves, and then we defined the shape of the worms by manipulating the p-scale values to describe which part of the worm was thin and which part was thick. And it's worth noting that we didn't really need to have too many points on our simulation curve to give us accurate looking collisions. So to create the simulation, we broke it down into 3 steps. The first step was to fill the box with about 1,000 worms. This dancing line that you can see here, this is actually our initial worm emitter. So we just had it kind of randomly moving around above the box, and this was used to create our initial set of worms that were used for the simulation. Once the box was full of worms, we then used that as a starting state of our simulation to push them up and outwards. And once the worms were pushed up and out of the box, we found that we were starting to run out of worms pretty quickly. And especially as the client kept asking for more and more worms. So rather than trying to fill the box with more worms in the first step, it was easier for us to just simply spawn more worms during the simulation. And we did that just from the center of the box. You can see it here. You know, it was completely off screen, so you can get away with doing that. The final simulation step was the interaction with the ground. So once we were happy with the spawning parts, re-simming the whole thing just to iterate over the behavior of what the worms did once they've landed on the ground seemed rather wasteful and time-consuming. So instead, we decided to set that up as a separate simulation. So as the worms fell out of the box, they were deleted in the old simulation and then respawned into a new one. This made the whole thing very easy to control and kept iteration time much, much faster. And once again, here is the final shot. Okay, so last up, we're going to look at some of the work that we did for HBO's Watchmen series. The sequence that we worked on was very effects and comp heavy, and it was a lot of fun to be involved with. The initial brief from the client was that there was going to be some kind of machine or device that was going to extract the energy and life force out of Dr. Manhattan. We were told that it couldn't look physical in any sense, that we shouldn't see bits of flesh and skin and that kind of stuff peeling off of him. The effect rather needed to look more ethereal and diaphanous, but it also needed to be visceral and look like it was utterly, utterly painful. Quite often with these type of magical and sci-fi type of effects, everyone walks away from the brief with a different picture in their mind of what it should look like. And because there's no real-world reference to base this off of, it all becomes very subjective. So it was very important for us to spend some time with our art department exploring all sorts of different options and possibilities of what this effect could look like. In this way, we could quickly iterate and refine the different and various looks at the concept stage before starting to do any expensive and time-consuming effects work. But once we had a good understanding of this effect and how it should look, we started doing some of effects development work. It was clear that we were going to need to generate a whole bunch of different effects and layers to create the final look. But I was also keen to try to ground this effect in some kind of physical reality. So we ran lots of tests using the flip solver to try and get something that looked like it was governed by some kind of real-world physics. So, ignoring my very questionable looking character animation for a moment, we eventually reached a stage where the various effects elements were starting to marry up and they started to look quite cool. There was still a lot of room for improvement, to be sure, but at this point it seemed prudent to continue the look development in a couple of the actual shots, because well, we needed to understand how these elements were going to integrate with the live action plate. And we also needed to start developing the look further in Nuke using various 2D manipulations and that sort of thing. So all the shot work that we did started off with match move geometry. It was extremely important to have skin-tight roto animation of our character, especially as this geometry was what we were going to be using to emit all of our effects elements. So if that geometry didn't match what was happening in the plate, the whole shot would fall apart. So when it came to generating our effects elements, to ensure that there was some kind of cohesion between all the different simulations that we were doing, we always started by creating one overall velocity field, which was used as the core force across the different simulations. This field was generated using a pyro simulation with various curl noises and fields around the match move geometry. So here we can see some flipbooks of some of the various particle simulations as well as the flip sim. And you can also see a type of wet map that was generated from those simulations. Because the effect we were aiming to achieve had extremely high velocities, we had to use a very high number of substeps for the simulations, which of course resulted in longer simulation times. So to try to mitigate that, we would often split up our sims into various smaller parts and then combine all of those caches into one render for the final thing. Here we can see some of the rendered elements that made up one of the shots. For this effect especially, there had to be a very strong collaboration between the effects and the comp team. As you know, a lot of this look was being developed in tandem both in Houdini and in Nuke. The artists had to really talk and collaborate with each other to try to figure out how we can best combine our efforts to come up with something that looked really cool. So I'm going to finish up by sharing you a breakdown that we put together of the shots that were delivered for this sequence. And that's it from me for today. I'd like to once again thank the team at Side Effects for hosting this presentation. And of course, I'd like to give a big thank you to all the crew at Framestore who contributed towards the work that we saw today. So thank you.